Hello everyone, this is Sujay, a third year engineering physics student at IIT Roorkee. This video assignment is part of the course PHN 313 Signals and Systems taught by Professor Mayank Goswami. In this video, I'll try to briefly discuss about the principles of signals and systems which are applied in the neural signal processing. The main focus of neural signal processing is the measurement of brain waves. Brain waves are basically the electrical impulses that occur in our brain when information is being transmitted among the neurons. Brain waves have been divided into four groups, which are shown in the adjacent figure, namely delta, theta, alpha, and beta waves, which are in the ascending order of frequencies. EEG, which is electroencephalogram, directly measures the electrical activity of the brain. EEG measurements employ recording system consisting of electrodes with conductor media, amplifiers with filters, AD converter, and a recording device. It can diagnose various diseases like epilepsy, brain tumors, sleep disorders, brain injuries, Alzheimer's disease, etc. Now, coming to the artifacts in EEG. The picture we see here is a typical output from an EEG machine, which is a result of four types of brainwaves, as we have seen previously, and it helps us in studying the functional state of brain and find disorders if there are any. If we want a detailed analysis of the brainwaves, we have to break down this output into the resultant of several types of brainwaves while removing the noise and artifacts as well. Artifacts are unwanted components that distort the EEG signal. We can reduce them through various methods such as improvising the electrode connection, avoiding movement using filter technique such as blind source separation, wavelet transforms, empirical mode decomposition, or using auxiliary information from other sources such as ECG, EMG, etc. Now coming to the time and frequency domains. The time domain represents how a signal changes over time. It is quite useful for showing transient and time localized features of a signal and for knowing when an event occurs in a signal. But it doesn't always reveal the underlying structure of the signal. If the signal contains multiple frequencies, like in this typical output of EEG, which is composed of different types of brainwaves, it is quite hard to tell their individual contributions from the time domain view alone. This is where frequency domain helps us. The frequency domain represents a signal in terms of its frequency components, showing how much of a signal lies within each frequency band. We can obtain the frequency domain of a signal from time domain by applying Fourier transform. The salient features of using frequency domain is that it reveals periodic components of a signal and useful for identifying dominant oscillations or patterns. While frequency domain is quite useful, it also doesn't show when specific frequencies occurred in time. Now, considering these two graphs, we can see these both are sinusoids. Since it has a frequency of 3, we can write it as, and having an amplitude of 1, it can be written as sine of 6 pi t. And since the second one has an amplitude of 2 and a frequency of 5, this function is 2 sine of 10 pi t. Now, the power domain spectrum of these two is the one which is exactly below of them. This shows just the amplitude and frequency. Now considering the third signal, which in first sight it would be a totally different signal, but it is actually the sum of these two. That would be sine of 6 pi t plus 2 into sine of 10 pi t. Now, if we apply the Fourier transform to the given resultant signal which is in time domain, we get two components. One which is of 3 Hz having amplitude 1 and the second one which is of 5 Hz having amplitude 2. Therefore, analyzing in frequency domain is much easier when it comes to these cases and it saves a lot of time. One more advantage of frequency domain would be getting rid of noises. The signals we see here are just the previous ones with random noises added to them. It would be quite difficult to even know the prominent function of the signal apart from the noises. But in frequency domain, we can just understand in a second that the prominent one is a sinusoid with respect to amplitude and frequency, and it has these background noises with low amplitudes at various frequencies. Since these broadband noises have a flat power spectrum, it is also referred to as white noise. Therefore, we can convert the typical EEG outputs to their respective frequency domains to know which brainwaves are prominent by checking their frequencies and their amplitudes as well. The noises look quite negligible in frequency domain as compared to time domain, since each noise adds up at every point of time, therefore corrupting the signal in time domain. Now coming to Morlet wavelets. This wavelet is composed of a complex exponential, which is basically a sine function, multiplied by a Gaussian window. This wavelet is closely related to human perception, both hearing and vision. Generally, these type of wavelet functions are designed for time frequency analysis. Essentially, they are sinusoids but are modulated by a Gaussian envelope by which they are tapered at the both ends. This bell-shaped curve ensures that the wavelet is localized in time, meaning it only captures signal information with a certain time window. By adjusting the width of the Gaussian envelope, we can fine-tune the wavelet's resolution. Here, we can see few wavelets which have different frequency but are almost having the same window length. As we see here, this wavelet provides temporal specificity with just do the Fourier transform with this wavelet instead of sine function and do the dot product of it with a given signal for a period of time and then convolute it. This provides us this retains the specific characteristics of the certain part of the signal, which in the case of sine function it just averages out whole of the signal. And one more interesting thing about this is if we apply the inverse Fourier transform on a power spectrum which has a Gaussian profile, we would obtain a Morlet wavelet. There are a few more advanced methods for frequency analysis, namely Wells spectral decomposition, in which we roughly estimate the power spectral density by dividing the data into overlapping segments. And coming to filter Hilbert method, the Hilbert transform is applied to convert a real signal into its complex representation. While in short-time Fourier transform, it is basically a Fourier-related transform used to determine the sinusoidal frequency and phase content of local sections of a signal, and it changes over time.